We're going to wrap up Chapter 5 by switching from that sensation side of things and focusing more on the perception side of things. We're going to focus on how we can put those sensations together, how we frame them, how we put everything into sort of a unified whole. And so we're going to be talking at first about depth perception. So continuing on with our discussion about visual systems, but we're going to be looking at how we can put things together and perceive depth. So you're going to find, again, this is very similar to our auditory system, where we could use our two ears to localize sounds. Now we can use our eyes to try and figure out how far away items are. And we have two different kinds of depth cues. So these cues can be monocular or binocular, mono meaning one, bi meaning two, and ocular just talking about how many eyes are required. So our binocular depth cues rely on the fact that we have two eyes placed at slightly different locations, so they're perceiving the world slightly differently. Monocular cues just mean that they don't rely on us having both eyes in different positions, so we could see those even if we just had one eye, or even if we were looking at something like a two-dimensional image, which is how I find it easiest to imagine these monocular cues. So let's start off with our monocular depth cues. So these are the ones that don't require both eyes to see. So I envision these as a lot of things that you could, say, get from a painting, something two-dimensional, or a photograph, where you don't need that sort of both eyes seeing slightly different images in order to get depth. We can just sort of look at something and get which one is further away based on some of these little clues or cues that help us figure it out. So the first of these is occlusion, and this is basically just the idea that things that are closer to you tend to block things that are further away from you. So if you're watching this lecture on your screen and you happen to have a pet, so maybe you have a cat, or you're like me and you have birds, so your pet might sit between you and your screen, blocking part of your screen from view. So they occlude your screen. And that can only happen because your pet is closer to you than your screen is. So you can therefore determine that the screen is further away, the pet is closer. So you can figure out relative distance based on which things block which other things. We can also look at relative height and relative size. So this is just when you're looking at two different things. So maybe you have a tree that's way off in the distance, and that tree looks to be about this tall. But then there's also a person who's closer to you, and they look to be almost as tall, if not taller, than that tree. You don't necessarily determine that it's a very small tree or a very large person. You would say that, well, this person is probably closer than that tree is, so we can assume based on size or height, what it should be. We could also look at, two cars, and one looks larger than the other, but we know that cars tend to be about the same size, so it's not that one car is significantly larger than the other, it's probably that one is closer than the other. Next, we can look at perspective convergence. This is another one that works really well with drawings. And so if you have ever been in an art class and they've asked you to draw a horizon line and a vanishing point, and then you draw something like a street or railway tracks that seem to vanish off into the distance. So I know I had to do a ton of these when I was in grade school, and it's not that railway tracks will eventually come to a point, it's that they look like they're converging off in the distance. So as they get further away, they look smaller, and it gives the illusion of them converging. So perspective convergence, this sort of melding off to a vanishing point, is what's going on here. So that's perspective convergence. We can also use our familiar size, kind of like our chat about two different cars, and if one car is closer or further away, it will look larger or smaller. Same thing with things like people. If a person looks like they are much, much larger, it's probably because they are closer. So you rely on having a basic understanding of how large things should be, and then you can sort of make or fill in the gaps from there. And the last one is atmospheric perspective. And this one is, again, nice, easy to visualize. If we think of, say, a photograph of the mountains. And so if you've spent a lot of time looking at pictures of the mountains, you might know that the stuff in the foreground, so maybe we have some mountains here, and then we have some grass, because I'm a fantastic artist. So we have sort of grass and flowers and stuff in the foreground. And then we have further away mountains that are in the back that are a little bit fuzzier. And so what's going on here is that things that are further away have more air. They have more of our atmosphere between us and them. So it gets hazy with distance. And we saw an extreme of this in the last little while with a lot of smoke days. So there was lots of smoke between us and things in the distance. So we didn't have to look very, very far away to notice that things were getting fuzzy and unclear. It could be as simple as something across the street was looking kind of fuzzy because there was stuff between us. So here, things that are further away have more air between our eyes and that item. So when we look at it, the things in the background tend to be a little bit duller in color. They tend not to be as sharp, so the lines will be a little bit blurrier. And then things that are up close, things like our foreground here, would be a lot more sharp and in focus and colorful. So all of those are pieces of atmospheric perspective. And so these examples are why a lot of our monocular depth cues work very, very well with things like two-dimensional images or paintings. They line up with a lot of the ways that artists would trick your eyes into assuming that something is closer or further away. All right. And then we can look at our binocular depth cues. So these are the ones that require two eyes, the information from both eyes, and it's because they're at slightly different locations. So the first is the idea of retinal disparity. And so objects are going to project slightly different images in slightly different locations on our right and left retinas. This is basically the idea that we have two eyes. So if we're looking down on our eye, so these are our eyes from the top, and we're looking at maybe our hand in front of our face. So I'm just going to draw like a mitten shape, because that's perfect there. And so our left eye is going to be seeing this side of the mitten, and our right eye is going to be seeing that side of the mitten, and it's going to project to slightly different places on our retina, and they're seeing it from slightly different angles. So our brain can figure out this slight difference between what both eyes are seeing to determine how close or far away something is. The closer something is, the bigger the retinal disparity. The further away it is, the less retinal disparity. And a really quick way to envision this yourselves is to hold your hand in front of your face and close one eye and then the other. And your hand will look like it shifts position just a little bit, and that's seeing retinal disparity. And if you move your hand closer to your face, you see a bigger jump between your left eye and your right eye. And if you move your hand further away, you see less of a jump between those two images. Convergence deals with the idea that as things are closer to our face, as we're trying to focus on things that are closer to us, our eyes have to look inward. I suppose I could have left my image at the bottom here with our two eyes, but as we move an item closer, our eyes will have to sort of look inward or converge again to look at that item. Whereas if we were looking at something further away, there's less convergence there. Eyes don't have to focus inward as much. And then things that are very far off in the distance are going to be very much closer to parallel in terms of our looking. So our brain can pick up on this degree of convergence, how much our eyes are looking inward towards each other, to figure out approximately how far away an item is from us. And then when we're talking about processing, this next section isn't specific to visual cues, but it is helpful to consider visual cues for processing, just because there are some that we can relate to very well. But we can talk about the difference between bottom-up and top-down processing. So with bottom-up processing, we start with the individual specific features of a stimulus. So if we're looking at an item and we're not quite sure what it is, maybe we start making note of what color is it, what shape is it, what texture is it. And you can start combining those specific features into more complex forms. So it's a circle. Is it a ball, maybe? And then eventually, from putting all of this stuff together, we can recognize the stimulus, we can figure out what category it falls into, and then interpret that object as a whole. As an example, we can look at this first of our optical illusions here. So we have this semi-ambiguous drawing. So we have an eye, we have a head, and then, okay, well, is this a beak or is it ears? And depending on what we identify this feature as, that'll tell us if this is a duck or a rabbit. But because we started looking at individual elements and individual shapes, this would be a good example of bottom-up processing. Top-down processing does the opposite, where we would formulate a hypothetical. So when we look at something, we would start interpreting it in terms of information that we already have or concepts that we already know. So the example for this one is an exit sign. So if you're in a building and there is a bright sign near a door, you might not be reading each individual letter of the word exit, but you would see a sign near a door and make that assumption that, yeah, it's probably an exit sign. So from context and previous experience, we know that this is an exit sign. We might check that it actually says exit, that it's not some strange marketing campaign or something strange like that. But we use our existing knowledge and the context and sort of the situation. We can double check certain aspects of it, but we recognize the stimulus. And so we can see sort of benefits and disadvantages to each of these. With bottom-up processing, it's a lot slower, but we can be more adaptive. We can look at things that are sort of ambiguous and maybe figure out what features they are that are causing that ambiguity. With top-down processing, we might make some assumptions that aren't necessarily correct. So maybe we assume it's an exit sign, but maybe it's an exist sign, and it's somebody who's campaigning to focus on, I don't know, a band or something. I don't know. They've thrown in an extra letter, and if we just looked quickly at it, we might assume an exit sign, but if we look closer, we realize that it's something else. So that kind of marketing would take advantage of our top-down processing to make us look twice at an item. Next, we can talk about our gestalt principles of perception, specifically our perception of form. And these are basically general rules that talk about how humans tend to put things together, how we tend to consider separate items and group them together and treat them as a unified whole. So Gestalt psychology focuses on the fact that the whole is greater than the sum of the parts. So when we look at a scene, when we look at the world around us, we don't just see individual components that are unrelated to one another. We use a lot of different sort of schemas, a lot of different mental maps and shortcuts in order to group things together so that we can start getting meaning from our environment. And the first of these is a really great way to start and show how we tend to group things and treat things in our environment. And we're going to do this by looking at ambiguous figures, some more optical illusions, because those are interesting. So the first of our principles is the figure-ground relationship. And this is basically just the idea that humans are really good at deciding what is the figure or the focal point of a scene and what is the background, what is that extra irrelevant information. And so we tend to very, very quickly organize scenes, organize our environment into central focus figures and sort of generic background that doesn't require a ton of attention right off the bat. And here our illusions at the bottom kind of play with that a little bit. So the one in the middle, we might decide that this is a cup on a black background, or maybe it's two silhouetted faces on a pink background. And this is what we would call an ambiguous figure-ground relationship. So we can't decide if the cup or the silhouetted faces is the figure, and so we hop between those two different ways of solving this problem. In this one over here, we can ask, is it an image of a face or is it a landscape of a person walking across a courtyard between some trees? And then this one over here is it a young woman looking away, or is it an old woman with a scarf over her head? So lots of different ways of deciding which part is the figure and which part is the background or remaining information. And that's how we end up with this ambiguous figure-ground relationship. I'm going to hop back here, and these 4 principles in the middle here actually get their own slide, so we'll cover those in a second. But I do want to talk about our principle of common fate. And this is one that I have only actually seen this year. So the principle of common fate is basically the idea that when things move and act together, we tend to treat them as a single item. And the best way to envision this is to think of a flock of birds flying. When we look at a flock of birds, they tend to move together in a pattern, in a predictable manner, more or less. And so we tend to treat the flock as the item that we're interested in. We will very, very rarely focus in on each individual bird that makes up that flock, but we might look at the movement of the flock as a unified whole. So that illustrates this principle of common fate, where those individual elements, those individual birds, aren't the important thing to our mind. The flock as a whole is considered more important and therefore the focal point from that situation. All right, now let's do these 4 with their own slide here. So our principle of similarity just focuses on the fact that we like to group things together based on similarity. So you probably see a triangle of small circles, and then either another triangle made the 3 large circles, or 3 large circles that stand alone. But in either case, we're grouping the small circles together, and then maybe we're going to group our large circles together too. So the things that are similar are treated as the same. For our principle of proximity, we would probably look at this not as 6 individual lines, but as 3 groups of 2. So we have 1 short line and 1 long line close together or in close proximity. So we would probably treat that as a group. And this would be another pair, and this would be another pair. So we group things based on how close they are to each other. Our law of closure basically says that we like to fill in missing information. So in nature, if we were looking at a human being, and we can only see them from the waist up, maybe they're standing behind a table, well, you wouldn't assume that they are just half a human being. You'd assume that they're a full human being, but we just can't see all of them right now. So we make that assumption of what is outside of our line of sight based on what we have in our knowledge already. So we would fill in or close off that silhouette with the assumption of what's missing. And so the same thing applies here, where we might assume that this is a circle where we can't see this one corner of it. So we still assume that it's a circle. It makes sense that it's a circle, even though it isn't quite closed. And very close to that, we have this idea of continuity. And this is where we assume that things move in a continuous pattern. So we would see a line from A to B and another line from C to D, rather than viewing this as sort of a little shark fin shape that goes from A to the middle and then down to C, and then another shark fin shape that goes from D to the middle and over to B. We would probably see this as 2 nice smooth lines that move continuously. And then the last thing we can talk about are our perceptual constancies. And this is the idea that we perceive things as being similar or the same and unchanging, even though they appear to be changing dramatically. The first of these is a fantastic example, kind of optical illusion-y again. But if we look at these 2 men sitting in chairs, we know, based on relative size and some other things like maybe the vanishing points in this image, that this man is probably closer to us and that man is probably further away. This man is probably not a very small man. But when we use Photoshop to cut this background man out and move him to the foreground, over here, this looks ridiculously small. He shouldn't be that small. That's overdoing it. But once we've taken him out of the context of the background here, he looks overly small because our brain isn't sort of assuming that humans are always about human-sized, and it's just the background that's creating that illusion. Once we remove those extra contexts, it kind of throws off our ability to hold on to these constancies. And so he looks even smaller when we violate some of those. Another good example of this is for the constancy of shape. So you're talking to a friend and they turn to look at something off to one side. So you had been looking at their face front on, and then you're looking at their silhouette. Their face has a dramatically different shape because you're looking at it from a different angle. But you don't assume that their face has changed shape. Their face is the exact same shape, you're just viewing it from a different angle. So the shape is constant, but your perspective is different. We can also look at brightness and hue. This one's really easy to envision if you think of wearing a shirt that is a particular color. And maybe the lights in the room that you're in now are nice, warm, soft lights. But if you went outside, you'd be under harsh, bright light. Or maybe if you were lit by candlelight, it would be very, very dim light. And with different lighting situations, your shirt might look like it's slightly different colors, different intensities, different brightnesses. But we know that you don't have a magical color-changing shirt. It's just the environment, the lighting conditions that are changing. And then the last one is our location in space. And this is the idea that usually when we're moving around in our environment, we don't assume that things are moving to meet us. We assume that we are the moving factor and that we're approaching or moving away from things in our environment. So if you're walking towards your desk, you don't assume that your desk is coming to meet you. You are walking to meet your desk. You know that it's not moving, even though with your vision, it looks like your desk is moving. You understand that you are the factor that is in motion and that your desk is stationary. So we use all of these different kinds of constancies, all of these different perceptual rules in our brains to start making sense of all the sensory information that we're coming in. And it's kind of neat to look at these because it starts giving us an idea of all of the extra information our brain is capable of processing and making use of in the background, which is a very nice setup for next chapter, which is our chapter on consciousness.